about that for a moment. So the outcomes that match to event C would be greater than 4. So if I roll a 5 or if I roll a 6, those two outcomes match to that. Event D is I roll a 1, observing a 1. So that's only one outcome associated with event D, and that is if I roll truly just a 1. Event E sub I is defined as I roll the integer I. So E sub 1 would have in it just one outcome, 1. E sub 2, one outcome if I roll a 2, and so forth like that. So that gives you a flavor of events. What we get interested in, and back to this, if we talk about the six-sided die, we say, well, what's the probability of event A, that I roll an even number? What's the probability of rolling an odd number? That's what we're going to evolve to. But for the moment, we're looking at events and different outcomes that match to events. Certain operations with events will result in the formation of new events. These new events will be subsets of the same sample space S as the given events. So we say event intersection. The intersection of two events A and B denoted by A, and then this is this inverted U, you could say, is the symbol for intersection, or just by putting the two A, B next to each other, is the event containing all elements that are common to both A and B. So let's see, if I had an event, let's see, my event could be that the weather was not, no, let me think. Why am I blanking on this? A could be the event that I rolled an even number, and B could be the event that I rolled a number greater than 4. And so what are the outcomes common to A and B? It would only be 6 if I rolled a 6, because 6 is the only even number that is greater than 4. Mutually exclusive, two events are mutually exclusive if A intersection B is equal to the empty set. So if I said event A is that, let's say with the even numbers. So I roll an even number. B is the event that I roll smaller than 2. Okay, so B as an event only has if I roll a 1, and that's not even. So the intersection of those two events is the null set, the empty set. The event union would be the union of two events A and B denoted by the symbol. Now here you have the flipped around, kind of like a U shape. Union B is the event containing all the elements that belong to A or B or both. So if I were to say A is the event even numbers, B is the event greater than 4, then A union B would be 5 and 6. Because 5, even though it's not in A, it's in B, and 6 is actually in both A and B. Okay, so to look at these different, and you've probably seen this before with the Venn diagrams and different sets notation. The complement of an event A with respect to S, all the possible outcomes, is the set of all elements of S that are not in A. So the complement of an event A, even numbers, on a die, six-sided die that's rolled. If A is even numbers, a complement would be all the odd numbers, 1, 3, and 5. So, and we note a few things about these definitions. An event A intersected with the null set, of course, is actually, that should be the null set, not a 0 there. A union the null set is still the set A. A intersection A complement is the empty set. A or not A is going to be, and there's different ways you can say that. The complement of A or not A is a different way to say it. A or not A is, of course, equal to the full outcome space. Not in the sample space would be the empty set. Not the empty set would be the full sample set. And then not, this is like a double negative, not A is, of course, going to be B. Okay. Addition to the learning checkpoints that you'll see throughout these presentations, I'll go ahead and put out that there's some textbook exercises you can do also offline. Go ahead and pause the recording and go ahead and practice the exercise just to make sure that you're understanding and tracking with what I'm saying as we go. Of course, now it's fairly simple, but as we get going on some of the later lectures and stuff, you may want to take a stop and check that you understand the material. And again, if you don't, I recommend that, so back to the philosophy of this, I'm going to be recording these lectures with the assumption that this is one way to hear the material, one reference for you to learn the concepts and practice it. The other is to go read the textbook, maybe with the textbook. It's your choice, your assessment to figure out how clear you are on the content. But this is one you checkpoint try and do a textbook exercise. Again, back on the Blackboard, you'll find a course outline. And in this case, I've pulled up just one of them. So we have in the course outline, again, that's an Excel workbook that tells you when we're going to be covering which topics. One of the worksheets in that Excel workbook indicates the textbook exercises associated with each one of these recordings, particularly, topic sessions. So probability exercise number 1, and here's the specific problem that I recommend that you go ahead and try and solve. And as you see, you go through all through the book with different exercises mixed into these different lecture presentations. Okay, so defining probabilities for events. We have our sample space, all the possible outcomes. We have events where we define a characteristic or a set of characteristics and say, what are the outcomes that map to those events? And now we go and turn our attention and say, well, what are defining the probabilities for different events? And there's different ways you can look at this and think about how is it that we're going to define these probabilities. Axiomatic, classical, a priori, meaning we can do it before we run any experiment, we would know this. Example of this would be with card games. If you go off to Las Vegas or wherever you go for gambling purposes, card games or anything rolling the dice, craps. You can say, okay, given 5-card poker game, what's the probability that you get a flush? 5-card poker game, what's the probability of 2 pairs? That kind of thing. You can figure those probabilities out before you play any games at all. Another way, and we're going to look at each one of these, frequency or empirical. This is kind of like the guy flipping the coin for 10,000 times. A posteriori, after the fact, basically. You're going to flip. You're going to do an experiment to figure out the probabilities of different events. And then there's subjective. You see this at the horse races, for example. Let me go through each one of these. So as we get into this, let's first level set and make sure, intuitively, I think there's some aspects of probability that are just, it without even saying it. For any event A in S, the probability of A occurring is a number between 0 and 1. There's not a negative probability associated. There's not a negative chance that it could rain today. There's not a negative chance that the Dow Jones will close at 0 today. It's always between 0 and 1. There's no more than there's a 100% chance of rain today. There's 99% chance of rain today. So a probability associated with these events, 0.99 or 1.0, any given probability of an event can be only between and inclusive. It could have a 0 probability of something happening. but the probabilities are between 0 and 1 inclusive. Probability of the empty set is equal to 0, and the probability of the full sample space is always going to be 1. Okay, so an axiomatic approach to defining probabilities. Suppose a random experiment has associated with it sample space S, all the possible outcomes. Probability is numerically valued function that assigns a number, probability of P of A, to every event so that the following axioms hold. Again, probability of A, always greater than or equal to 0 for any event possible in S. Probability of the events over all the different events that happen, all the different outcomes rather that happen in the sample space, that's always going to be 1. Now, if you have different events that are mutually exclusive, there's nothing common between those events, and they add up to the full sample space, the full set of all possible outcomes, then the probability of the union of those events is equal to the sum of those probabilities. And we're going to come back to that one quite a bit more as we get into working with probabilities. But again, the probability of the union of mutually exclusive events is equal to the sum of the probabilities for each one of those events. Okay, so classical approach to defining a probability: if an experiment can result in n equally likely and mutually exclusive ways, and if n of A of these outcomes have the characteristic A, then the probability of occurrence of A, denoted as P of A, is defined as to be the fraction. Probability of A is equal to n of A over the total number of outcomes, n. So go back to throw a dice, a six-sided die, and let the characteristic A be that the number rolled is even. So what's the probability of A? Again, even roll would be 2, 4, and 6. N of A, in this case, would be 3. There are 3 outcomes that map to an even number. And the number of sides possible on this particular die is 6. So there's a 3/6 chance or 1/2 chance of rolling an even number. That's an outcome. So that's the classical approach. An example: experiment consists of tossing a fair coin 3 times in sequence. What is the probability that exactly 2 heads will occur? Okay, remember the sample space was this, so all of these different outcomes, 8 different outcomes, that's the size n. And our A, our characteristic of A, as we've defined it here, the event A is exactly 2 heads. So exactly 2 heads, I can look at it and say there's one that has 2 heads. There's an outcome that has 2 heads. You may not see my arrow. HTH has 2 heads. HHT has 2 heads. And THH has 2 heads. So 3 out of these 8 outcomes meets the characteristic defined as event A to exactly 2 heads. Alternatively, then the probability of one of these is 1/8. So you could say the union of the probabilities is 1/8. That's the associated 1/8 is associated with HTH. There's a 1/8 chance of getting that particular combination. There's a 1/8 chance of getting an HHT, and there's a 1/8 chance of getting a THH. So in total, that's 3/8. Okay, defining, let's keep going, frequency of empirical approach. Okay, so this is kind of like the flipping the coin 10,000 times, that in the long run, you would expect it to become the probability of an event that is happening. So if an experiment is repeated or conducted n times, and if a particular attribute A occurred f of A times, that's the frequency, then an estimate for the probability of an event A is defined as, and that little hat there is a little